Okay, well, thank you for that introduction, and thank you for the opportunity to talk to you this afternoon, wherever you are, and congratulate you on this really nice initiative and being able to carry it on forward, and hopefully it will carry on for many years. So for those of you who don't know who I am, my name's Dave Haddleton. I'm at the University of Warwick in the United Kingdom. Warwick is right in the middle of England, and we're probably best known for doing a lot of what you would call ATRP, which normally uses copper as a catalyst. But we also use Cobalt, and I've used Cobalt for a lot longer than copper. And we're always trying to get some control over the polymerization. And more recently, we, like everybody else, has had to turn our attention to making everything in the most sustainable way we can, which is obviously of increasing importance. Hence my title. So I'm going to start by talking a little bit about transition metals in biology. Then I'll talk about Cobalt-2 in something called catalytic chain transfer polymerization, which I've been doing for actually 35 years, and it's commercial. Many people will use the products that this is used in most days of their life. And then two little areas where we've used copper, one with emission properties, which is quite interesting, and one where we've used the chemistry to get very, very tight control that allows us to get sub-2 nanometer domain block copolymers. Then I'll finish on talking on where we've moved back to, really, after quite a number of years, on anionic polymerization of dienes and monomers from renewable feedstocks, and with a particular attention on life cycle analysis and making the chemistry more sustainable and doing it in sustainable processes. And I'll talk to you a little bit about doing chemistry in flow rather than chemistry in batch. That's my plan. So why am I talking about transition metals in biology? Because transition metals and metals are used to catalyze many things. And this is a polymer conference, and many of the polymers that we use in our everyday lives have got some metal that's involved in the catalysis, where it be PET, where you'll have a Lewis acid, tin or antimony, polycarbonate, all the polyethylene, all the polypropylene that you use will either have transition metals and main group metals. And what sort of interests me, I'm a transition metal chemist, is my PhD, and I see all of these people talking about metal free this and metal free that, and we need to go metal free because metals are bad. And metals aren't bad. Some metals are bad, and some organic molecules are bad. So ricin is pretty toxic, but that's got no metals in it. Phosgene, that's pretty toxic, and there's no metals in it, but we use it to make polycarbonate. So what I want to do is just start off by looking at why I don't think metals are bad. In fact, metals are very good. And then, because in fact, all of the polymers I'm going to talk about will use metal as catalysts or initiators, and especially for our younger people watching or listening, please don't think metals are bad things. Some metals are bad. So cobalt in biology, this is vitamin B12. Now, my guess is not all of you listening to this could tell me that it was cobalt in vitamin B12. Many of you might have done, but you would have forgotten the fact on the back of your cornflake packets, in whatever language you look at, you'll have cobalamin, which is this, vitamin B12. And vitamin B12 is a porphyrin. It's a corin, actually. It's got a double bond missing, which is actually quite important. It's octahedral, but it's got a square planar 4 nitrogen ligand in there. And then you've got an alkyl group that goes from Cobalt-2 to Cobalt-3. That's how the chemistry works, and that's how we use it in polymer chemistry. You've got this stuff around here. This is mainly just to make it water soluble. These are as well, which is very similar to what we're going to do in our polymerization catalysts. We just add things on the side to change the solubility, but we leave the metal bit where the business takes place, where it is. And you've got this axial ligand, which is just a nitrogen, which comes from a biological nitrogen, but we would use pyridine or some other nitrogen base. And we have a recommended dietary allowance for vitamin B12. It's very small. So it's very small, and it's in pretty much every cell in our body. And so it's a very low concentration, and it's very effective. And we only have to replace it because as you get old, you lose your skin and your hair, basically. So it doesn't really get killed. So it's not just the cobalt in doing all this chemistry. It's an extremely effective catalyst. Now, copper. Now, many people that do raft will start their talks by saying, well, the problem with HRP that the copper is toxic. However, there's 179 proteins that I found reference to that contain copper. There's even books on copper proteins and copper enzymes. There's even reviews, copper an essential metal in biology, really in current biology. And so copper's in all sorts of these things, and it exists in exactly the same way that we're going to use it in polymer chemistry. It's in a protein or a peptide, and you'll have a tetrahedral copper 1 usually, or copper 2 compound in the middle of that, and it's doing some chemistry and it's holding the protein in the right place. And both copper 1 and copper 2, because I'll be talking about both copper 1 and copper 2, and I'll be showing you that copper 1 actually is pretty unstable in aqueous environment in the presence of amine ligands, and it disproportionates. I'll come back to that. So again, don't think copper is always toxic. And in fact, we have a recommended dietary allowance for copper, depending on how old we are. And again, it's relatively high. And in fact, copper 2 salts are classified in the United States as generally regarded as safe by the FDA. So if you go to that database, and there's not a huge number of compounds classified as GRAS, but copper 2 salts are one of them. So it says copper is an essential trace element, etc., etc. In Australia, you've got the same from their Ministry of Health. Copper is widely distributed and it's essential, really. So again, when I'm telling you chemistry that we use with copper 1 and copper 2, we do remove the copper, and it's not difficult. However, if you don't remove the copper, it's not necessarily going to be that harmful. In fact, I often say that the most toxic copper is if somebody makes a bullet out of copper and shoots you with the copper bullet or a copper brick, and they actually throw the brick at you. But in your body, it's not necessarily as dangerous, and many people will allow you to think. So having looked at that, how do we use these transition metals in polymer chemistry, and why would we want to use them in the first place? So Cobalt 2 in catalytic chain transfer polymerization. So the catalyst we're going to use is this. It's called Cobalt. And if you remember the structure of vitamin B12, it's quite similar. We've got Cobalt 2 as drawn. Cobalt 2, it's in square planar with these 4 nitrogen ligands. It's got this strange boron difluoride, but they're there to make it into a heterocycle, to make it acid stable. So this catalyst is stable at pH 1 at 80 degrees centigrade, which is quite amazing. Without the boron, you can use it with methacrylates in organic solvents, but as soon as you put some acid, the catalyst will fall apart. And for those of you who want to remember your inorganic chemistry, Cobalt 2 is D7 low spin. What's quite important, if you're looking for a catalyst, you have to have a D7 low spin. We don't actually know why it has to be low spin, but if you change these ligands to oxygens, they'll go high spin, and they won't work in this way. And we're using this in a very similar way to vitamin B12. So a low spin cobalt complex, we're using it as a chain transfer agent to replace a mercaptan, and the monomer to cobalt ratio is 1 million or more than 1 million. That means its chain transfer constant coefficient is about 40 to 50,000, whereas a mercaptan will be about 1. Now, again, for those of you not familiar with free radical polymerization, a mercaptan is regarded as one of the most efficient chain transfer agents there is, and they're used commercially all the time. So the chain transfer coefficient of, say, benzene will be 10 to the minus 6. So we've got a compound here that's 1, 2, 3, 4 orders of magnitude better than the best chain transfer agents. So when we use that, that means we need 4 orders of magnitude less in grams or moles to get the same effect. And when we see the series of GPCs, we'll see with no or 0.3, Cobalt will have 23,000, and by going up to 10 parts per million, we'll take that molecular weight down to 800. So this is really good for getting very small numbers of N. And what it also does, I'm not going to go through the mechanism, but the way it works is that the majority of chains are initiated with a hydrogen atom, which come from the cobalt, and the terminal end is a vinyl group. So our oligomers have got hydrogen, and they're just integral numbers of the methacrylate, and we have this vinyl group on the end, which is quite a special vinyl group. So these are the first raft agents. So again, many of you might think raft is about sulfur, but the first raft agents made by Graham Mode and Ezio Rizzardo were these. So this will act as a raft agent, because when a radical attacks this carbon, it puts a radical here, and this is asterically hindered because it's got a methyl ester there, really. So it'll be probably a little bit difficult for you to picture that, but in a normal methacrylate, this would be a methyl group, but we've got a polymer chain. So because of that steric hindrance, you get fragmentation, and that allows us to make blocker polymers. It allows us to do all sorts of different things, really, which I'll talk a little bit about. So you can do all methacrylates. I've just picked one here. This is a glycidol methacrylate, which when we use CobF with a normal free radical initiator, V601 is the methyl ester equivalent of AIBN. We use that because the radical is then resembles a methacrylate as opposed to a methacrylamide, but you can use AIBN. Half-life is about the same. So reaction conditions would be about 70 degrees over less than 24 hours, but we could leave it for 24 hours. And we'll end up with this polymer structure. So the alpha end has got a hydrogen atom, which comes from the chain transfer, and the omega end has got the vinyl group. And here we've got two sites for further reaction. So we can do some reactions here, or we can do some reactions on the epoxide. So we'll ring open that epoxide to do various things depending upon what our application is. And if we look at the NMR, we can see that the vinyl group, this is quite a low DP monomer, so it peaks pretty sharp. The vinyl group, so it's slightly different from the monomer, so you can still measure, especially this one here. So you can, this little peak here is monomer actually, and this is the oligomer. And again here, this little peak here is some monomer, and then this peak is the product. So we can measure the conversion by NMR, which is quite usual. We change the amounts of cobalt, and we'll change the molecular weight. So notice these molecular weights are pretty small. So the blue one with 5 ppm, it's about 1,000, 1,100 mn. And then just to prove to you that the structure of our oligomer is what I said it was, we can look at the MALDI, and the difference here will be I think it's 142, which is the molecular weight of glycidol methacrylate, and we see just one N group, and so these beautiful. The dispersity of this is not narrow. The dispersity will be typical for free radical, 1.5, 1.6. So that's why it's not a sort of beautiful distribution in the MALDI, but we just see one lot of chain ends. Some of them will have the primary radical, but just a small number will have the primary radical fragment. And we've published a lot on these, and these are used in a glossy magazine. So if any of you've got a glossy magazine on your desk, the chances are that the high gloss coat has been made by an emulsion polymer that started off from a high acid content and high styrene content emulsion made by Cobalt chemistry. Then it's quite a complex slide, but I want us to, this is a chemistry that I'll talk about. And I've taken this from a 3M website. So 3M have done something quite, well, I think is very clever with this. So many of you, if you've gone to a dentist in the last 2 years, you will have one of these molecules in your mouth. I know I have, right? So my dentist used these products, and these products came from 3M in the United States. And this is from their flyer. It's called AFM, an addition fragmentation monomer. So the dentists in the UK and probably the dentists in your country will know the word addition fragmentation monomer, which is quite cool, really, because that's raft. However, there's no sulfur in this, so which is also quite interesting. So how does it work? So this is there. You can even get a video, which I haven't got the video to show you, but they've got this AFM monomer. So the polymerization that takes place in your mouth. Well, actually, I'll do the chemistry first. So you make and we do this chemistry ourselves as well. So you make a very low molecular weight polymethyl methacrylate oligomer by Cobalt. So it's got a hydrogen on the alpha end and this vinyl group on the other end. You distill out dimer, MMA dimer, and trimer and tetramer actually, but in this case we need the dimer. You hydrolyze that with potassium hydroxide. Very simple. You just reflux it for a couple of hours. You get methacrylic acid dimer. You then react that with glycidiol methacrylate to do the ring opening, and you end up with this cross linker, which is a dimethacrylate. You can obviously do all sorts of chemistry with this. And then here is the fragmentation site. That's the raft site. So that's a raft agent. That's the raft bit. This will then cross-link. So then after the dentist has drilled out the hole in your teeth to fill it, they will do some photopolymerization. It will mainly be a bunch of different diacrylates. This dimethacrylate will cross-link, and this AFM group, while the light is on, will break and form, break and form, break and form, break and form. And so it ends up in the least stressed environment in the final product, which is your filling, really, and that will give strength to the filling. And you know, I haven't got the mechanical data or chemistry to show you, but my proof really is that all dentists use it. Why? Because it gives better performance for their customers, which are the patients, really. So dentists do raft, but they don't do sulfur, and this is made with a Cobalt process that has come similar to catalytic chain transfer polymerization. So what do we do that? So my first sort of foray, I won't spend too long on this, but we'll be doing this in flow, and flow is considered to be more sustainable way of producing things than batch, and we'll be flowing the reagents into that. This is a thermal reactor, and then we will do the chemistry in that. This is a plug flow reactor. Also doing this thing, which I quite like, where we flow the reagents up into the middle, we thermally equilibrate that at the temperature we require, and each one of these holes is a little batch reactor, and the batch reactor's then got its own stirrer. So all of these stir with the overhead stirrer at the same rate, but as we push it through, it goes into this one, stirs for a bit, and then to the next one, into the next one, into the next one, and this really improves the mixing as opposed to plug flow going down a single tube. I haven't got time to do a lecture on that, but the improved mixing, especially in free radical polymerization and catalytic chain transfer polymerization, will give us a narrower dispersity. So we do that in flow. Then we're interested at the moment in translating the technology of dental composites into 3D printing. So 3D printing, photo 3D printing is almost exactly the same technology as dental resins and dental composites. You have diacrylates and you have fillers, and you use photo initiators, exactly the same photo initiators usually, and some dyes to get resolution. So what we do here is what I've told you before. We take methyl methacrylate. We now use a very simplified version of the catalyst. So we use cobalt acetate with dimethyl glyoxime. So here we make the catalyst in situ because we're not using acids. We distill out the MMA dimer. And we do this in like ½ kilo at a time. Then we'll make the methacrylic acid dimer, and then we ring open that with glycidiol methacrylate to give us our raft agent, and then we put that raft agent into the 3D printer. So we're generally using very, very cheap 3D printers, £300–400. We put about 10 in my lab, different types, because what we need to be doing is use these as additives for existing formulations. We also use them in bio 3D printing as well, but that's another story. And what we're doing here is that 3D printing is the realm of the house and the small part. So you can make an Eiffel Tower as long as it's a small Eiffel Tower, right? You can make the a shoe sole, you can make a bicycle, parts of bicycles, but what you can't do is make car doors. And you can't make car doors because the as you make that, you'll build up some internal stresses, and those internal stresses will then cause a little bit of distortion. And as you go to bigger and bigger parts, that means they won't be completely flat. Now, that's probably okay if I want to make a table or a desk, but it's not okay for a car door because I need the precision of the door shutting exactly the same way every single time. So there's a limit often on the size that this type of 3D printing can do. And so what we're trying to do here is to decrease the internal stress in the same way the dentists are, but not necessarily to increase toughness, but to increase the size of the parts we can make with improved tolerance. So it's one area that we're using Cobalt. The other area that we published this time last year with my good friend Frank D'Agosto was in Lyon, was to make block copolymers of ethylene and methacrylates. So Frank's group and the group in Lyon are very well set up to do high pressure chemistry, probably as good as I've ever seen anywhere, certainly in Europe, and they do make a lot of polyethylene. And so what we wanted to do here was we would make the oligomers of whatever methacrylate we want. So we were using methacrylic acid and methyl methacrylate and a combination statistical polymers of the two, and then to try and make a block with ethylene to introduce polarity into our polyethylene. And this was published in Angewandte last year. So the strategy here is, so what Frank does on a daily basis is they'll polymerize ethylene with a free radical process, normally in emulsion, but not exclusively in emulsion. So they'll be doing an emulsion polymerization of ethylene, and then make polyethylene. And then they're very well set up to characterize the polyethylene by a high temperature NMR and thermal analysis. So our experiment was we would put in our oligomers, and N would now be maybe 10 or 15 or 20. And what we wanted the polyethylene radical to attack there, which would produce a radical here. Now, if that was another methacrylate, I'd end up with fragmentation, a RAF process. I end up with a living polymerization. Well, anyway, we're going to go to this, and this could do a few things. We can either just carry on propagating, so we end up with polyethylene, like a three-arm star with one arm methacrylate, two arms polyethylene, or it can just terminate by abstracting a hydrogen atom, which would be ideal, because then that's got an AB block copolymer where the polyethylene block is however long that was, and we control that by the ratio of initiated to monomer, or the pressure of the monomer actually, and we control the length of the other block by whatever we decided to make. And we also decide the composition of the other block, because we can make a butyl methacrylate, or we can do stat polymerization with methacrylic acid, or we can do the addition fragmentation method, which is what happens with methacrylates. Turns out we get the abstraction, and I'll sort of go through how we distinguish between these three in a moment. So the polyethylene adds there that radical, then abstracts a hydrogen atom from somewhere, and we end up with an AB block copolymer. One of my favorite bits of evidence is the DSC. So what we've got here is polyethylene with melting temperature of 104, and then we mix polyethylene with the PMMA macromonomer without doing any chemistry, and we see the melting temperature of the polyethylene stays the same, whereas the product we get from the two is the melting point changes quite a lot. And the same in the on this experiment here, so we see the TG change as well as the melting point. The NMR, and again, the NMR can be quite detailed, but that's where Leon are experts at looking at the carbon-13 NMR of polyethylene and branch polyethylene, and so they were very happy to be able to assign these D peaks as these peaks here in the middle of the molecule. So we have now produced a block copolymer of polyolefins, polyethylene, with a methacrylate, which can be any methacrylate, pretty much, just by using radicals. Right? So there's no controlled polymerization. There's no living radical polymerization. And one of the things I'd say at this point, that's actually not necessarily a bad thing, because many of you will work on living radical, RAFT, ATRP, maybe nitroxide, and it's quite sobering to think that of all the polymers that are on your desk or in your room at the moment, 0 of them will be made by living radical polymerization. However, radical polymerization and non-living radical polymerization is all around you. Living polymerization, there'll be some of that on your desk, but that'll be made by living anionic or living cationic. So even though living radical polymerization has served me very well in an academic career, from an application point of view, it's disappointing, and actually we have to admit it has been pretty useless really in making stuff. Whereas if I'm using a free radical process, that's really what we need to do to get it into our lives. So I'm going to move now from cobalt to copper, and 2 little stories about how we use copper. We use copper in 3 different ways. So we will use copper 0 with copper wire, and I'll talk about that. And we're normally using hexamethyl tren or a tertiary amine ligand in an organic solvent. We use it in water, which I like a lot, where we use copper 1, but the copper 1 disproportionates, and I'll show you that on the next slide, actually, to copper 0 and copper 2. We have to wait for it to disproportionate, and then we're using copper 0 again. So here we use copper 0, here we use copper 0. None of them are copper 1. And photo-induced, we use copper 2. So we pretty rarely use copper 1 anymore. And when we use copper 2, we use these LED arrays, which we like a lot. And I'll come back onto that, where we photo-reduce copper 2 to copper 1. Copper 1 then disproportionates to copper 0 and copper 2, and the chemistry progresses. So I'll start with the aqueous media and why I think this is quite good. And let me see if I can get this to work. So what you're seeing here is a solution of hexamethyl tren in water. I don't think any sound's coming on this, so that's okay. And then when the button's pressed in real time, some copper 1 bromide has been added to that solution. Now, again, if you remember your inorganic chemistry, copper 1 is white. Copper 1 is not blue. Copper 1 is not green. It's D10. And the colors of transition metals are because you have an electron missing. So copper 2 is D9, blue or green, blue in water, green in organic solvents. So what we've seen here in 30 seconds is the copper 1 has reacted to become copper 2. And if you look at these bits of black stuff, I'm not sure at the top, that it's copper 0. At the time, we thought you had to degas. You actually don't need to degas. But here we're just bubbling with some nitrogen to make sure there's no oxygen in there. And I'll come on to the next slide on why you don't need to deoxygenate. And then once we've done that, we have no copper 1 left. It's just copper 0 and copper 2. We then add the monomer and the initiator. If you have the monomer and the initiator present during that 1 minute, then you get 2 different processes. You get ATRP, and you get the mechanism that we're following in water, which is not ATRP. So you would get 2 different polymer distributions and pretty much a mess, really. But if you're prepared to wait a minute, and then add your monomer and your initiator at this particular moment in time, the results in the dispersity and the control are quite spectacular, really. So don't think you cannot do living radical polymerization with copper in water. It's the best solvent, in my opinion, there is. And you can do it in the presence of anything, really. So you can do that in the presence of ethanol, in the presence of sugars, in the presence of pretty much any impurity. You don't really have to purify anything. Now, oxygen is quite interesting. So what's happening when we do that, we disproportionate the copper 1 to copper 0. Bearing in mind, we've just made some brand new copper atoms. If there's any oxygen, they get instantly oxidized back to copper 1. And that will instantly disproportionate back to copper 0. So your oxygen is actually consumed very fast. And at the time, we wanted to find a way to prove that. And we had a particularly brilliant student in the group, Evelina, who's back as a Utopia fellow with us and currently in Brisbane at the moment. She's probably not listening to this, so I can say that she's brilliant without becoming too self-conscious. And I said, well, we need to be able to measure it. And we found this little thing here, which is sold by a German company, by Pyroscience. And it's essentially sold for you to go around lakes and rivers and put it in to see the oxygen content, to see whether or not fish or biology can occur, or whether the oxygen levels have got so low that the fish can't survive. So essentially, you just poke it in and it gives you a reading. You can wave it around in air and it will just give you the oxygen level of the room. So actually, that's also quite a good measure of ventilation when you're trying to see whether your room is ventilated enough to go and teach to 200 undergraduates, and you're a bit worried, where you were a couple of years ago anyway. And so it collects data points, and then once you've collected all your data points, you just plug it into your computer and just downloads information. And it turns out you can get it works by infrared emission. It's quite clever actually, but only costs about €2,000. But you can have one where the cell is inside a syringe, which is brilliant. So people like me don't break it. We broke one in the first hour, and we had to go back to them and say, well, do you have one that's a bit more robust? And they said, oh, you should need one in the needle. Well, thank you very much. So then you can poke that through a super seal. It's protected by the needle, and it just gives you an instant reading of the oxygen level. And you can put in, actually, we've not found an organic solvent that you can't put it in, really. And then when you do that, you will get this reading of the oxygen. So if you do that in the reaction that I was just showing you, the oxygen just plummets in 5 seconds, right? So in 10 seconds, it's gone to less than 0 milligrams per liter. Right? And then you can do all those different things. So if you've just got copper bromide in water, the oxygen level obviously doesn't change. As soon as you add a ligand, you then make your copper 1 unstable. So your copper 1 is unstable, and it just disproportionates, and that consumes the oxygen because you've got copper atoms. So now we would, this is 2 seconds. This is quite a fast depletion of oxygen. And I would urge all of you who are worried about oxygen levels in your reactions, get in touch with Pyroscience. I wish I had shares in them, but I don't. And you can measure the oxygen level. So we need to do this in anionic polymerization as well now. And it turns out, here I've got 3 different reactions, which are methyl acrylate, doing polymethyl acrylate in diamososa solvent. We've got hexamethyl tren. This is our initiator, and we're using copper wire. So essentially, you probably see here, if we've got some copper wire wrapped around the magnetic stirrer. And you'll also see that this one's dark green, this one's a bit lighter, and this one's much paler. And all we've done here is we've got exactly the same reaction, but we've just used smaller and smaller vials, which meant there was less air in there when we put the super seal. So the more air you've got, the more copper 2 you get. As you reduce the amount of air, you get less copper 2. And when you fill it up, you just see no headspace. The oxygen level is depleted. So the easiest way to deoxygenate, you just fill up your reactor. In our case, we use vials. Now, again, in industry, you would generally fill up your reactors almost to the top because you don't want to waste space. But most academics, you've got a 250 round bottom flask, and you've probably got 50 or 100 mils of liquid floating around in the bottom. So academics are pretty bad, myself included, at using all the space in their reactor. However, if you do, you don't have to bother to deoxygenate because it self-deoxygenates in a very quick time period. Because that was a very boring monomer, a very boring polymer in DMSO as our solvent. And if I use that for something a little bit more interesting, we're again using copper wire, again using vials, we're again just filling them up almost to the top. But now we're using a fancier initiator. So in all of this chemistry, as long as I've got an alcohol, I can esterify it with this commercially available acid bromide, which we do. Our undergraduates make these. In fact, our undergraduates do reactions of using copper-1 disproportionation to make polynipam. We have no Schlenk lines, or we don't even bother to measure the oxygen level. And we did it a couple of weeks ago, and they all make polynipam with dispersity less than 1.1. Anyway, in this particular case, we want this initiator, because this initiator, for those of you familiar with this, you may not be, it's an AIE, which means when it associates, it induces an emission. So if it's not associated, if it's just freely soluble, this moiety will not emit light. However, when it associates or gets above a certain concentration, the act of association causes a very bright emission. It's beautiful, really. I mean, it's very not discovered by myself. It's discovered by Benzon Tang, and it can be used in all sorts of different applications. Well, here we make these tetraphenylethylene with one alcohol by doing this pretty simple reaction. We then esterify that to make our initiator, and then we just grow the polymer from there, depending upon what we're going to do. In this particular case, we're using copper 0, hexamethyltren, and a polar solvent, a DMSO or IPA probably in most cases, and we can polymerize any acrylate. This is an acrylate, not a methacrylate, and then we polymerize that off. And our alpha end has got the emissive group, and we've changed the this. We make blocker polymers depending upon what we want to do, so we can self-assemble that with the emissive group on the outside. And it's first published with polyacrylamides for bioimaging, actually. So essentially, once the molecule, if you could persuade the molecule to aggregate in a biological setting, then immediately it just lights up, right? So, and if it's freely dissolved, it's not lit up. So with polynipam, if you can get it to precipitate, once it's precipitated, it lights up. If it's not precipitated, it doesn't light up. So it's a really nice switch, and the emission is really bright, very, very bright. So what we're doing here is make this methyl acrylate, tertiary butyl acrylate, and then chop up the T-butyl acrylate to get us our hydrophilic hydrophobic blocker polymer. Dispersity of these is less than 1.2, usually less than 1.1. There's pretty much zero termination doing it like this, and so you can imagine here we would self-assemble this and get our, it would be emissive because it aggregated. We can then do this in water as well. So the previous slide was about doing this in with relatively hydrophobic monomers. Now we're going to do acrylamides. So acrylamides and water-soluble acrylates. Same principle. We make our initiator, but we now do that disproportionation. We take our copper-1 bromide, we disproportionate with hexamethyltren. And water, typically in ice, but it doesn't really matter. Especially when we're doing NIPAM, we don't want the exotherm to precipitate, so we remove the heat. We can use co-solvents. So in this particular case, our initiator is not soluble in water, so we'll dissolve that in a co-solvent that is miscible with water, and we'd add the solution of the water miscible solvent with the initiator in to the solution of the disproportionated water, disproportionated copper in water, and you can polymerize well, any acrylamide you want. We'll polymerize in a few minutes, really, and the dispersity you get again is less than 1.1. You can use acrylates, peg acrylate, hydroxyethyl acrylamide. This turns out it's always the best monomer. I don't know why, but the narrowest dispersity and the best control you see, even in raft actually, with in water is with hydroxyethylacrylamide, NIPAM, morpholine, dimethylacrylamide, any of them really. Now it's in polymer chemistry. So what does AIE mean? It means as I increase the concentration, all of a sudden it lights up. And if I decrease concentration, it stops emitting. So the emission is dependent on the concentration, on the architecture, and on the temperature. And so lots and lots of control. And the latest one, which is, I just did the proofs for this in macromolecules this morning. So we've used that with our copper wire. We've then used it in water. This is our third way of making polymers, which is photochemically, where now we use copper-2. And so this would be used for hydrophobic acrylates and methacrylates. So here we've got all sorts. I know it's quite small, but we've got very long chains. So we'll have oleol, we'll have lauryl, we'll have butyl, we've got tertiary butyl, benzyl. And in this chemistry, we're doing it with LEDs. So we either do it with a 96-well LED display. This is 470 nanometers blue. Also works with 365. Also works with red, actually. Red light is not supposed to work, if you believe the papers coming out from some very eminent people in the last few weeks. But we have red LEDs and it will just work fine. So we'll need to publish that soon. But here's with blue. Red actually is lower energy than blue and it's deeper penetrating. So again, it all fits in with the sustainability theme. And we want to use photons rather than heat to do chemistry. Here we've got 96-well plates. We cool that because these LEDs generate a lot of heat. And then we actually cool the reactor as well because we don't want chemistry to be doing it. We want photochemistry. We can also do that in flow. So we have a flow reactor here. And you can see the light here. We use the whoever that is, you might want to do mute because I don't think it's coming from my office. And I don't know what the language is either. So anyway, we're pumping that through the solution. It doesn't polymerize in the syringe, but as soon as it gets in our light block, it will start to polymerize. And we can also do that. This is a different reactor. This is a Vaportech flow reactor. So now the LEDs are in here, and we've got everything going into that. And this will use blue LEDs as well. So we have the same LEDs in this reactor and that reactor. And then we can look at it in the Lumidox flow and the Vaportech flow. So the Vaportech one is for scaling up. So we can just be pumping it through that for as long as you want to make as much as you want. So just to show you the differences. Again, I'm not going to go through everything. So we're taking about 1.5 hours, 2 hours, depending on the wavelength. So we can change the wavelength 365, 405. For those of you who don't know, 405 is a particularly interesting wavelength because that's the wavelength that most 3D printers work at. So if you open up a 3D printer, they've normally got 405 nanometer LEDs in there. So 405 we use a lot. So you can then translate this into a 3D printer and use the same wavelength. Dispersities less than 1.20. And if we use the scale up, the Vaportech, this machine here, we can get well, spot on molecular weights, so really spot on, and we can get very good dispersities. We can also do it in this type of thing where we do, this is normally used by biochemists to do cross-linking, and we just flow it around there. And from that reactor, we will get these dispersities, and you look change the residence time, the flow rate, etc. And so very, very easy to translate between flow systems and very easy to do this by photochemistry. Then what we do in flow on this one, we are then functionalizing our polymer as it comes out by reacting with a thiol. And I've just showed you some MALDI. So we get, this is polymethyl acrylate, again, pretty much perfect, no termination. And then when we add in the thiol, in this case, it's thioglycerol, you get a nucleophilic displacement of the bromine, and you get the change in molecular weight. And so you get almost perfect functionalization. Now, the second bit where we use copper is to make these very small domains. And this has been published in 2 papers, which from this student has finished now, Ellis, and we done this with Paul Topham at Aston, who's our SACS expert. These are the world records. So these papers, which is sub 2 nanometers, no one, this is the lowest nanometer domain size. And Paul Topham gets very frustrated because no one cites us because we're not really in the microphase separation club. But nevertheless, if you are in the micro separation club, you might want to look at these papers. Why are these so small? We've now got an initiator that's got a fluorine. So this is a discrete molecule, and we're going to change the length of that, change the amount of fluorine. We polymerize off using our UV system using copper-2. We use T-butyl acrylate, and we then hydrolyze to get acid. So we've got a fluorinated block, a discrete block, and we have an acid block. So these are very, very different in polarity. Because this chemistry, I know you probably won't all believe me, but because this chemistry really does give you the most precise control over the length that you can get, then DP5 and DP6 and DP11 are distinguishable. So 5 and 10 are completely different. So if you use most living radical polymerizations, DP5 and DP, well, first of all, you can't make DP5. And if you could, you couldn't distinguish between 5 and 10 or 20 and 25. It's just too small. You can distinguish between 10 and 30. But so what we're doing here is we get very, very narrow polymers. We get very discrete chain ends, and the dispersities are pretty much as low as you can get. Then we would cause them to do phase separation, and we do SACs, and then we can change the length of the fluorinated group. This is C6, C8, C10, so we've got 13, 17 or 21 fluorines. We can change N by going 5, 10, 15, 20, 25, and then we do we cast them as films, we anneal them, and they will self-assemble. Some of them won't, they go disordered, some of them will be lamellar, and some of them will be hexagonal. And we can then map that space, and by mapping that space, we can then get the phase diagram. So here we've got disordered, then we can move into hexagonal, and then we can move into lamellar. And just turns out that if we use the right ones, which is the smallest, it'll be probably the F21 with the smallest DP10 probably will give us the smallest domain size. And I'm not going to show you the whole of this thing, but we will do SACs, and we get these, and these 3 peaks show you it's a lamella, and something like this looks like it's hexagonal. And what we can do is, if I can turn off my laser pointer, I can even show you a video of this. So what we're doing now here in the spectrum in the top right, we are doing the SACs in real time by changing the temperature. And when we get to about 80 degrees, we'll see that order disappears. So we go from lamella and the order goes away. Then when we cool that down, I'll just skip along a bit. So now we're cooling. And then when we now get to below 80, we start to see some order come back, but the order now returns as hexagonal. So we can, by the annealing, we change the way that the polymer orders by changing the polymer length. And by doing that, you can literally get down to sub 2 nanometers, which is important in photolithography. And again, I won't go into details like that, but you can see we're using this chemistry, everything from biology to mobile phones. The last few minutes, I'll try and do this in 5 minutes, is I switch back to anionic, because as I mentioned earlier, although many people in universities do living radical polymerization, it's not very useful really. Whereas anionic polymerization and cationic polymerization has got multiple products that most of us use every day of our lives, and to be honest, it's much better at controlling the polymerization. So here we started off making polydienes, and we started off using polymyrcene. So myrcene is a natural product, it's a renewable resource, and we were polymerizing it by ionic polymerization, although you can polymerize it by coordination and by radical polymerization. We all use polyisoprene and polybutadiene in many products in our lives. One of the things you may or may not remember about anionic polymerization of dienes is that we can control the stereochemistry by controlling the, just changing the solvent, to be honest. And so we've got myrcene, we'll have these isomers, and isoprene these and butadiene these, really. And what we want to do is we want to control the amount of this 1,2, because these double bonds will do subsequent reactions at different rates. And what we want to do is selectively react the 1,2 and then hydrogenate out the 1,4. We switch from myrcene to isoprene to butadiene because even though myrcene is from a renewable resource, and so everybody thinks, oh, that's fantastic, it's renewable, it's massive energy, so its impact on the environment is huge because it comes from something called pinene. You have to pyrolyze it 160, you get a low yield, then you have to distill it. So actually, if you look at the life cycle of that monomer, renewable is not good. And it turns out butadiene is actually a negative energy monomer. So by using butadiene, it's a negative effect on the environment. So we've now switched to polybutadiene at the insistence of our sponsors. Isoprene is about energy neutral. So even though it's from a petrochemical, it's negative energy. So we're on myrcene and now do butadiene. We do that polymerization. Control of the N group is actually trivial in anionic. You'll see many papers in radical where we did this to do that, and we ended up with 75% N group modification. Isn't this really good? Well, here you get 100% really. So we're targeting relatively low molecular weight because it's dispersants. So 2000, we get full conversion. We're not using high vacuum lines, we're just using normal glassware, and so these dispersants are pretty good. And then you can terminate that just by a ring opening with propylene oxide, butylene oxide, any epoxide, and you change the molecular weight a little bit, but you get very good dispersant. And this is myrcene with a variety of different N groups, and you see by the Maldi that as we terminate with different things, we just add that molecular weight, and it's perfect, 100% really, especially at this molecular weight, which is quite low. We can even get primary amines. This will then give you a primary amine after a deprotection, and so this allows us to control the N group much better than living radical, to be honest. And then we do that in flow. So what we're doing here is we are doing anionic polymerization in flow. We then actually, this is electrochemistry, so we modify it electrochemically or we modify it photochemically. And the photochemical modification we do, so bearing in mind we can change the chain end to be a ring open epoxide, so we've got a different chain end. We've now got control over this 1,2. Here we're doing a maleic anhydride 2+2 photo addition to introduce some maleic anhydride, which we then ring open with an amine. That's quite conventional for this type of chemistry. And then we hydrogenate it all in flow. So what we've now got here is a flow hydrogenator, and this is Will actually. So we've got those two systems there. So we do the polymerization, then the photo functionalization, and then it flows into the hydrogenator. Hydrogen's made electrochemically, and then we fully hydrogenate out all the double bonds. And then we have a benchtop NMR. This is our NMR, and we flow it through the NMR at all the different stages. And at every different stage, we get optimization of the reaction in flow. And what we're working on, and I think our new research fellow Kansu is in the audience, and she'll be joining us on December the 1st. Her job is to help then get the machine learning to get our NMR and our online molecular weight measurements to then inform the pumps and the temperatures and the hydrogenator about what to do to optimize the reaction. And that's where we are. And by hydrogenating it out, we change the TG and we change the thermal stability. Again, this product is designed for an automotive lubricant. So it has to perform above 300 degrees centigrade. We don't want no oxidation, and we want no reactivity or cross-linking. Really. So that's what I've got to tell you. This is our group last Christmas, a whole bunch of people who very talented. We've worked with Leon, with Frank D'Agosto, and a student who's graduating there called Florian. My daughter actually did a postdoc with Frank, and Florian and my daughter used to go skiing before COVID wiped out the Alps. So not just thanks to Florian for chemistry, but for helping look after my daughter while she was there. Paul Topham and Matt Derry at Aston, we couldn't do any of the X-ray without them. And a lot of the AIE stuff has been done with the AIE Institute in southern China, Tinghan. And our funding is mainly from Lubrizol, but a bit from Syngenta and a bit from EPSRC. So thank you very much for your attention. I'll be very happy to answer any questions. Please.
Okay, thank you very much.